Hello, I'm Grace Wesson, and today we're going to be talking about power series and Taylor polynomials. As a review, these are the 6 most important formulas for you to know in these problems. Normally, you won't be given one of these outright. You'll be given something like cosine of 7x cubed or something like that, in which you will substitute 7x cubed for x. So keep that in mind as we will be going through worksheet problems in this. All right, now on to Taylor and Maclaurin series. In this formula, fn of a is the nth derivative of the f of a function, a being the center. A Maclaurin series is essentially just a version of the Taylor series, except your a value in a Maclaurin series is always going to be 0. In problems where you encounter Taylor or Maclaurin series, this a value will be given to you in the problem. And if it's a Maclaurin series, it will be stated outright, and you will know that the center is 0. The center in a Maclaurin series is always 0, and keep that in mind during tests and quizzes, as it's a pretty common mistake to forget that. Now this is the Lagrange error, also known as Taylor's inequality. Note that these two formulas are pretty similar, except this one makes more use of n plus 1 than this one does. Usually for formulas where they ask for the error, they will give you a domain for x. In order to find the m value, that is the absolute value of the maximum of the n plus 1 derivative of f. Taking the absolute value is key here because you are essentially just finding the maximum values for all of these. Because you want to get the largest value for this part of the inequality as you possibly can, so that this is always less than this. If you want to look at it this way, it's essentially a pessimistic view. You're going to want to overestimate, per se, your error. Now x minus a here means, so a here is the center, right? Whereas x is the farthest value in the domain from a. And you take the absolute value of that distance. Again, this is a largest value. This is also a largest value. So you're basically overestimating your error, getting the largest value possible for your error. That's just kind of a rule of thumb for this inequality, which can help you memorize it. Okay, so go ahead and try this problem on your own. Keep in mind the formulas that we learned, and keep in mind the application of the more abstract concepts. Now this is a fairly simple problem. You can just use one of the memorized formulas to come up with the series. You should immediately recognize constant over constant plus an x term is probably the geometric series power series formula. The purpose of us choosing this problem was to emphasize checking your endpoints when finding your interval of convergence. Now, in order to find the interval of convergence, you want to do the ratio test, right? Because this is a geometric series, essentially. And when does a geometric series converge? A geometric series converges when the absolute value of your r value is less than 1. Now, we put soft brackets here because when you plug in an x value for each of these, you get divergent. So these are soft brackets. But if you had gotten convergent, these would have been hard, the square brackets, basically. All right. When you are converting this to a power series, it needs to be in the form 1 over 1 minus your ratio, so that you can make use of the geometric series formula, which is essentially what we did here. Okay, so why don't you try this next problem on your own? This is another pretty simple problem. You simply evoke the Maclaurin series formula for cosine of x and substitute 3x cubed for x, as we discussed in the first slide. This is just an example of why learning those formulas is so important to make you more efficient on tests, quizzes, and ultimately the AP test. We choose to present this problem because we wanted to emphasize the separating of the constant from the x, right? Because we have 3x cubed, all of that to the 2n. But we want to separate the negative 1 to the n and the 3 to the 2n, which is what we did here, in order to get x all by itself, which will make it way easier to solve for this ratio test here. Now we got r equals infinity and then soft brackets around the two infinities. All right, try this problem and make sure to keep in mind the formulas that we learned earlier. There are a couple of very important things that I would like to point out to you. First, when you see sign x squared in the limit, you should be able to recognize that you can apply one of the formulas you have memorized, just like we did in that last problem. So that's where this part came from, and then instead of putting x right here, we put x squared because you're given x squared in the original problem. After you recognize that, it is a great idea to write out the first couple of terms of the sequence, because you will likely notice cancellation in the numerator. This is typical of problems like this, to have it cancel out in a way that if you did not know this series here, you would be completely unable to solve it. Lastly, as good mathematicians, you probably see in advance that the denominator cancels the x's in the numerator. But don't only write out the first three terms in this problem. Write out more than you think you will need, just in case. Another common mistake here is that when you're canceling, you get caught up in all the action of canceling, and you forget about this denominator, right? So you're left with x to the fourth over 7 factorial, and make sure that you don't forget the simple math that you've learned earlier. It's very, very common. Okay, go ahead and try this problem. The center that you're given here is a equals 1, and your n value is 4. And then you are given an x domain. For the first part of this problem, I wanted to point out how the coefficients in the table, here and here and here, are not combined. In this problem, you don't have to worry about making a general formula. But if you had to make a general Taylor polynomial formula if it were asked of you in the problem, it would be helpful just to leave the coefficients as is. For example, on a multiple choice test, you would want to leave it like this, because it's very likely that the answer that you would be given in a multiple choice test would be this same thing, but if you had combined the coefficients, it might be more difficult to memorize. And then you eventually get this Taylor polynomial. This problem is a little difficult, so we didn't have you come up with a general formula, but this is just a tip for general purposes. Alright, go ahead and try this problem. Okay, the m value in this is the maximum absolute value of the n plus 1 derivative of x, which is graphed right here. So you can see that at x equals 2 right here, the absolute value is much greater than at x equals 4. You can just see this from visually graphing it. Normally, for Taylor inequality problems, you are going to be given a calculator, which is very, very helpful. Okay, so right here you can see that the absolute value of f to the n plus 1a is greater than it is at x equals 4. A is your center given in the problem, which we can see here is 1, so we can just plug that in. And then we find the x value furthest away from it in the domain. So our value is going to be 4 for that x. Next, we need to, you would most likely be using a table of values, like you did in the last problem, to find out what the value of f to the n plus 1 is at x equals 2, which give you this value, and then n plus 1 equals 5. And then once you plug that into your calculator, there you go. If you were paying attention, you learned the importance of using our Maclaurin series formulas, as well as the reasons behind the Lagrange error and the Taylor inequality, and why they are so useful in estimating what we know about Taylor-Maclaurin series and power series. Additionally, you learned how to find the interval and radius of convergence for a power series through the use of the ratio test. You learned how to apply formulas that you already know to diverse and complex problems to make the most out of the knowledge that you already have. Thank you. I hope that what we have taught you is helpful, and I hope that you do well on the AP test.